It's that time again. Hello and welcome to another very exciting See the Change USA webinar. My name is Vincent Weiss. I'm the manager of product and training development with See the Change. And today we are going to talk about the fourth part in a four-part series talking about all the things from the unit Energy 1 from the See the Change USA curriculum. Today we're going to focus specifically on thermal energy. So a few housekeeping items for this webinar. There will be no audio or video, so if you've turned on your video, if you can shut that off because you will not need it. So we're going to communicate using the chat box feature. If you do not see the chat box option, move your cursor to the top of the screen and a drop-down menu comes down. Click on the ellipse on the far right, and then you'll see an option for chat box. Click on that, and the chat box should pop up. And at any time, do feel free to put in any questions or comments. And throughout the session, I will be glancing for questions. And there will also be a question and answer session at the very end, and we can discuss any questions you have. This session will be recorded, and the recording will be put on both the Physics Lab and the See the Change USA Edmodo group. And the PowerPoint will also be made available on the See the Change USA Edmodo group. And if you stick around at the very end of the session, I will tell you how you can be a member of that group. So the purpose of today is first and foremost to build your confidence in physics. You are all excellent science teachers, but our goal is to make you world-class middle school physics teachers so that you can be fully confident in the topic of physics. And this is also to help you bring some high-level physics content to the middle school mind. A lot of these concepts that we are going to talk about are usually concepts that students will see much later, not because it's difficult, but just because they're just concepts that are just kind of burst off to the later stages. So we're going to take those concepts and bring it down to the middle school mind. So who is this for? It's for specifically teachers looking to take their students to a deeper level of understanding, and for teachers who do not have an extensive background in physics but would like to master the concepts. So you don't need an extensive background in physics, but just by watching this, you will gain a greater understanding of the topics of thermal energy than probably 90% of middle school physics teachers, or middle school teachers, I guess. And this is also for teachers looking for alternate ways to explain concepts to students. So throughout, we are going to show different animations and hopefully come up with some good ways to explain some of these concepts to students. We're also going to be talking about different common misconceptions to help you identify and diagnose these common misconceptions and ways you can help your students get past some of these common misconceptions. And as it turns out, concerning on the topic of heat and thermal energy, there's quite a few common misconceptions. So we will talk about some of those. So without any further ado, let's get started. Actually, no. What we'll cover? Well, we're going to cover specifically the content found in these lessons, so lessons 1.4.14 through 1.4.16. These are the last few lessons in Energy 1. We're going to discuss what happens when it appears the energy in an object vanishes. So if you drop a ball and it starts bouncing and then it stops moving, what happened to that energy? Then we're going to differentiate between internal energy, heat, and temperature. These are very specific terms that are always used when we talk about thermal energy, and they need to be clearly defined, and because they imply different things. And then finally, we're going to discuss the factors that affect the heat capacity or the ability of an object to store thermal energy. And then finally, we're going to have a question and answer session about the content found in these specific lessons. So let us get started. So imagine you have a ball that starts with a lot of energy and starts bouncing until eventually it kind of dwindles down and stops moving. So the question is, what or where does this energy go? This seems to be in direct conflict with the conservation of energy, which states that energy cannot be created or destroyed. It must be transferred from one place to another, which we call the conservation of energy. Is one of the most important principles in all of physics. But here we have this example of this ball that drops and falls and bounces, and then it stops moving. So it seems as though the energy in that system is completely gone. Or is it? Upon closer inspection, and this is an excellent thing to do with your students, to actually give them an object and let them drop it and then see what it does, and try to come up with every single observation they can about this specific thing, and to ask them with this specific question: where does the energy go? Because it must go somewhere. Where does it go? And a few things that they'll notice. One, it makes a sound. So there's some type of something going on with the sound. And also, it produces some sort of vibration on the ground. If they're close enough to the object, they can feel those vibrations. And if you had really sensitive equipment that could measure right where that ball bounces, you would be able to measure a slight change in temperature. And the temperature would increase, so there would be a little bit of heat. So as it turns out, as the ball falls, this sound is going off, there's some vibration, and then there is heat. So all of those pieces, the sound, the vibration, the heat, are forms of energy that's leaving the ball and being transferred from the ball to another different type of form. And all of these different things, sound, vibration, and heat, have to do with the motion of particles, so they all fall into the category of thermal energy. Now, when we think about thermal energy, typically we think of heat, and heat is a type of thermal energy. So to prove that heat is, in fact, energy, we remember that energy is the ability to do work. And I want to remind you to stress this again and again and again, and beat it into your students' mind, that when they think about energy, they immediately need to think about the ability to do work. So they need to think about work and energy at the same time. So whenever they see some type of energy and they say, oh, this is an energy, have them prove what type of, that it's actually energy, by giving some way that that energy can conduct work. Because if something cannot conduct work or do work, then it can't be energy, because energy is the ability to do work. So how does heat do work? Well, if we have this balloon and we put a flame under it, well, the gases in that balloon start heating up and they expand. And as they expand, they stretch the balloon, doing work on the stretchiness of the balloon. And in fact, if you heat anything up, it will expand. So this gas does work on the balloon, so heat does work, which means that heat is a form of energy. This is the sure signature that energy exists. Here's another simple example. If you take a container of water and you start heating the water up, it will produce steam, and that steam can be used to rotate this little flywheel. Now, this seems like a little simple demonstration, but this is in fact how every coal and oil and nuclear power plant actually produce energy. They use some medium like burning coal, burning wood, burning oil, burning nuclear particles to heat water, and the water produces steam to turn some turbine that generates electricity. So this was really an example of a power plant. This is exactly how power plants work. They work by converting thermal energy into mechanical energy, and that mechanical energy can be used to create electrical energy. So thermal energy comes in two distinct flavors, if you will. First flavor is called internal energy, and the second is called heat. So let us kind of define these terms, starting with internal energy. So here we have a rock, and if we zoom really close into that rock, we will see this rock is made of particles, and we will notice that the particles move around. And if we could look at every single one of these particles, which is very difficult to do because they're really small, but if we could look at every single one of these particles, we would notice that they all have some kinetic energy. And because they interact with each other, they have some form of potential energy. And if we added all the kinetic energy and all the potential energy from all of those particles, we would have the internal energy of that object. So internal energy has everything to do with the jiggliness of all the particles that make up a substance like this rock. So now what about heat? Well, imagine we have these two objects that are one is hot and one is cold, and we touch the hot object to the cold object. Well, immediately energy will flow from the hot object to the cold object, and we call this energy heat. So heat is defined as the flow of energy that moves from a hot object to a cold object. Now, this brings up some strange phenomena. So imagine we have these same two objects, but now let's imagine that both of these objects have the same amount of internal energy. So if we were to add up all the kinetic energy and the potential energy from all the particles in both the small object and the large object, we'd find that the total energy internally is the same. Now, if this were the case and they were the exact same material and we were to touch the small object to the large object, something strange happens. Heat flows from the small object to the large object, even though it was at the exact same internal energy, until eventually it slows down and stops so that no more heat transfers over. And if we separate them again, well, now they have different internal energy because energy from this object moved into this object. So now this has a smaller internal energy than this larger object. And this is really strange because when we think about how an object, how energy flows, we think that energy must flow from high energy to low energy. And this is what we see with potential energy. An object always moves from high potential to low potential energy. But it takes work to move an object from low potential energy to high potential energy. So one would think that heat would flow from the object that is high in energy to the object that is low in energy. But as it turns out, this doesn't always happen. Sometimes it does happen, but this is not, it doesn't happen in general. So what's going on here? Well, imagine we have these two boxes, and let's say we have no idea what their internal energy is. All we know is that one object is hot, or it's at a higher temperature, and another object is cold, and it's at a lower temperature. If we were to touch these two together, we'd immediately notice that heat will flow from the hot object to the cold object until eventually they both reach a common temperature, and they have the exact same temperature. So this actually tells us something pretty profound. That heat flows in the direction from high temperature to low temperature. And it is not the energy inside the object, but it's the temperature inside the object that actually defines the direction heat will flow. Now, what is interesting in this case is that we talk about heat flowing in one direction, but is it possible for cold to flow in one direction? Well, cold is actually would be, I don't know, negative energy. So there's no real such thing as cold flowing from one thing to the other, but we match the energy flowing from one object to the other object. So one would say, well, you know, if you put your hand close to a gallon of milk that was in the refrigerator, you can actually feel the coldness coming from that gallon of milk. So what's going on? Well, in this situation, the actual sensation of cold is the feeling of heat leaving your hand going to the milk. And this is completely counterintuitive, but it's physically what's happening. Energy is transferring from your hand to the milk, and that sensation we pick up as this feeling of coldness. So an interesting question that students bring up all the time, so I would encourage you to bring up this idea that cold doesn't really move anywhere, but it's actually this heat, this energy that is heat moves from one object to the other object. But As it turns out, this is always true. Heat will always flow from high temperature to low temperature. So in a lot of sense, temperature is more valuable than the internal energy of an object. So the big question is, how does temperature relate to internal energy? Why does it seem that these things are different? Should they be different at all? Well, let's take a look. So the problem comes when we assume that objects are made out of these perfectly round, solid sphere balls. And if matter was actually made up of these things, then temperature and internal energy would pretty much be the same thing. But real matter is a little more complicated. So here we have a water molecule. Because of its asymmetrical shape, it can store energy in a multiple different ways. So it can store energy in rotational motion as rotational kinetic energy. It can store energy in the vibration of the atoms in this type of vibrational potential energy. Or it can store energy by physically moving around, which we call translational motion or translational kinetic energy. And as it turns out, it is this translational motion. Temperature is most affected by this type of motion. So it's for this reason that we say that temperature is defined as the average translational kinetic energy of a substance. So here let us take a look at a few different substances that store the same amount of energy. So here we have this array of water molecules, and all of the energy is stored in rotating these molecules. Notice there's not much movement between the molecules. So if you were to touch this substance, it would feel actually cold because it doesn't transfer much energy at all. Even though these things can be spinning arbitrarily high, so they can have actually a really high amount of energy, but they're going to have a low temperature because they're not moving with much of that translational motion. If we look instead at particles that are moving like this, notice how they are moving and jiggling about, but they're not rotating. If you were to touch this type of substance, it would feel really hot because all of that motion is easily transferred into your hand. So this substance would also have high energy, but it also comes with a high temperature. Now, if we take a look at these situations, these two situations, and we say that temperature has to do with all these things moving around, what if we make those things perfectly still so that there is no molecular motion at all? Well, this would represent the coldest possible thing that there can be. Absolute zero motion would be the coldest thing something could actually be. In this case, no energy could be transferred at all. So we call this absolute zero. Whenever a substance is made up of particles that have zero energy, this is called coldest possible temperature. And believe it or not, it can be expressed in terms of units of Celsius and degrees Fahrenheit. So this absolute coldest temperature happens at around negative 273 degrees Celsius or negative 460 degrees Fahrenheit. So it's actually impossible to cool something down below this value. So a temperature of 275 degrees does not exist. That would it would imply that somehow these particles are experiencing some sort of negative motion, which of course is impossible. So this is the coldest an object can actually be. Now to wrap up, temperature tells us how much internal energy is stored specifically as translational kinetic energy. And the more translational kinetic energy in the particles, the more likely the substance will transfer heat to neighboring substances. And this is why heat always flows from high temperature to low temperature and not necessarily high energy to low energy. So let us wrap up these two ideas with a very standard experiment in heat. So suppose we have two beakers filled with different amounts of water. And what we're going to do is we're going to heat both of these beakers with the exact same heat source so that the internal energy of both sources increases at the same rate. But we're really interested to know how will their temperatures increase. Will one increase faster than the other, or will they increase at the same time? Well, if we actually do this experiment, we'll see that yes, the internal energy increases, but notice that the temperature of the smaller amount of water increases much faster than the temperature of the larger amount of water, even though it's been given the same amount of internal energy. Well, if we were to continue heating both of these things to the boiling point of water and then immediately remove the heat, we notice something very interesting. So notice it started boiling, so the heat is removed, and then we continue heating this, and then it starts boiling, and then the heat is removed. Now we notice that though they are at the exact same temperature, the amount of internal energy in this substance is much greater than the internal energy in this substance. So we say that this water has a greater heat capacity, or a capacity to store more heat. So the more mass a substance has, the more thermal energy it can store, and this makes good sense. So you have more water, so there's more particles to absorb that energy, and there's more available ways to store that energy. So it can store more energy. So when it comes down to the classic mouse versus elephant question, this question is, if you were to put these two animals in this cold environment and to measure their temperatures over time, which one will stay warmer longer? And well, there are a few factors in play, like the mouse may have a really high metabolism and can burn through food really fast, and the elephant may have a slow metabolism, doesn't burn through food as fast. So if we were to just ignore all the other things except for their specific heat, or their heat at a very specific moment, well, we'll see the elephant has a greater capacity to store thermal energy, so it's going to cool down slower. Now, this is obvious with these two animals, that we see that the bigger elephant has more thermal energy, so it's going to cool down slower, but it's not so obvious when we look at these two objects. So we compare the burning match to this big iceberg and ask the question, which object has more thermal energy? Now, this is a fun question to pose to students because it appears as though the match must be super hot. And it's much hotter than that big iceberg. So obviously, it seems as though the match has more thermal energy, because if we touch both, one's going to burn you, one's going to cool you down. But as it turns out, it's the iceberg that will have more thermal energy, or has internal energy, because it simply has many more particles. The particles on average are probably, well, on average we can say are moving slower, but if we add up the energy from all of those particles, we'll see that it has a huge amount more total energy than this tiny little match, simply because it's much bigger in size. So this is one of the big distinctions between temperature and internal energy. Here we have an object that has a high temperature. Here we have an object that has a high internal energy. But as we see, heat will always flow from high temperature to low temperature. And never would we expect the iceberg to heat up the match, but we always expect the match to heat up the iceberg. But when we look at the total energy of both objects, we'll see that this actually has more internal energy, simply because it has many more particles inside it. So here is another interesting case. We see that mass has an effect on heat capacity, or how much heat an object can store. But what if we take two objects? Here's a piece of copper, and here's water. And let us now assume they have the same mass. So now we're not looking at a very specific, now we're comparing how is heat stored in different substances, copper and water. If we were to heat both of these substances and measure their temperatures, we would see something very interesting. We would see that the temperature of the copper shoots up quite fast, whereas the temperature of the water slowly increases, even though both objects have the same mass. So it seems as though water is more resistant to changes in temperature than copper. And we call this quantity that describes this resistance specific heat. So if we have equal amounts of copper and equal amounts of water, copper has a specific heat of 0.385 joules per gram per degrees Celsius. I don't want you to look so much into the units. We're not going to talk about the units, but I want you to compare this number to this number. So 4.179 is about 11 times greater than 0.385. So this means if you had equal amounts of copper and equal amounts of water and you started putting heat into both of these objects, water will be 11 times more resistant to changes in temperature. So we see that specific heat, which affects heat capacity, is very much like the inertia of heat and temperature. It resists changes in temperature. So the greater specific heat an object has, the more it resists the change. The more mass an object has, the more it resists changes in temperature. And water, liquid water, has one of the highest specific heats of any liquid. So it makes water an exceptionally good, makes water an exceptionally good source of regulating temperature. So we know that our Earth is covered with over 70% of water. Without that water, we would have much drastic temperature changes between the hot and cold of the day. Our hot days would be much, much hotter, and our cold days would be much, much colder. But since the world is mostly covered with water, all of that water helps to regulate the temperature of the Earth. So we really do not experience extreme temperature changes here on Earth. Not only that, but most living things, just about all living things, like plants and animals, are mostly made of water. This is not by accident. It's because water is a really good regulator of temperature. And if you're going to rely on things like blood flowing, you will need very specific temperatures to which all of living tissue can operate. So water is one of the most amazing substances, and this is just one aspect of how amazing it is, because it is so resistant to changes in temperature. It is one of the factors that makes life possible, and one of the big reasons why scientists look for liquid water on planets to see if it can actually sustain life. So this is about all I have today to share about heat. So now I want to open it up to any questions that you might have, any comments, concerns, anything you have. Okay, so it appears as though there are no questions. If you think of any questions later on, say, shoot, I wish I would have asked, do feel free to send me an email. I'll give you my email in just a few slides here. So I just want to point out that this recording in PowerPoint will be made available on both the Physics Lab under the Teacher Content Training and Energy 1, and it'll also be made available on the See the Change USA Edmodo group. To become a member of the See the Change Edmodo group, if you are not already, let me change my share screen. So I want. All right, so here is the home page of the See the Change USA. This is the physics lab. From the physics lab, click on resources. Then you will see this tab for links. Click on links. And here is a link to the See the Change USA Edmodo account. So by clicking on view, pop-up menu will come up. All right, and you'll have to create a free account if you haven't already done so, but after you create a free account and log in, you will be directed to a join request page. So since I'm already a member of the group, I can just go to the group, but if you're not a member, you'll say send join request, click on that, and then we'll be notified and we will accept you and put you into the different small groups to access all the materials, to include the PowerPoint and this recorded webinar for all of the energy. So you can go back and watch all of those webinars and you can access all of those PowerPoints. So really awesome place. So do please join and send your join request if you're not already a member of the See the Change USA group. Let me go back to the share. All right. So for additional teacher training content support, do look at the physics lab under teacher content training for the different units, and you'll find fun videos, more webinars, and different type of engagement resources. So this is all to help you and in all different ways. Or you can go to the See the Change USA Edmodo group. There is an open forum where you can collaborate not only with the See the Change staff, but also with other teachers that are working through the program who've perhaps come up with good solutions to the problems you are facing. So really excellent place to communicate with people who are working through the very same things. And there you can post questions, comments, concerns, ask for help on anything you want. It's a really good source. Or you can send me an email at vincent.weiss@seethechangeusa.org, or send Laura an email at laura.horvath@seethechangeusa.org, and we will schedule you a one-on-one session to where you can meet with either me or Laura about anything, and we can work out any content training or anything that you need if you're not feeling confident in the physics that you're teaching. So just another way to boost up your confidence in physics. Or give us a call at 1-888-843-0671. We'd love to hear from you. So there are no other questions. I want to thank you all so much for joining us, and we will see you all next time. Thank you so much.